All right. Now I'd like to talk about a really important concept in the design of recursive algorithms, and that's called memoization, which is just memorization. Okay, I don't know why they call it that, but the idea is we want to memorize the results of previous recursive computations so that we can reuse them and save ourselves from having to redo certain recursive computations. So this is really a time versus space trade-off. We're using more space to save ourselves some time, but that's really going to come in handy. Okay, it's a very good trade-off in this case. So to really elucidate this and to show where it helps, I want to talk about two different recursive implementations, and I want to show you that their time complexity is vastly different until we use memoization. So the first one is the factorial sequence. So factorial is something that is naturally defined recursively. So n factorial is n times n minus 1 factorial. That's a recursive definition, right? Now, of course, we also have our base case or stopping condition, which is that 1 factorial is equal to 1. Excellent. So if I go ahead and convert this into code, what I'll say is def fac n. And I'm going to break our style convention for a moment. I know we're only supposed to return from one place, but I'm going to return from a couple places just so that my code matches my math a little bit better. So I'll say if n is 1, return 1. Okay, so factorial of 1 is supposed to be 1. Otherwise, you're supposed to return n times factorial of n minus 1. Okay, so now I can actually back up and show you last time when I was comparing the factorial to powers of 2. So if I print the powers of 2 to the n for n in range 1 to 11, and then I compare this, now I actually have an implementation of factorial. I can compare this to factorial for the same range. Let's look, and we can see that, all right, yes, for the first 3 powers of 2, they beat the factorial, but then once we get to 4, factorial is larger than 2 to the n. And after that, man, it really starts to pull away. It swamps the heck out of 2 to the n. All right. So let's talk about another sequence that is amenable to a recursive implementation. That is something called the Fibonacci sequence. So let me just quickly create some placeholders for the elements of the sequence. So I've got 1, 2, 3, 4, 5, 6, 7, 8, and I think 9 is probably enough. Okay, so the first element of the Fibonacci sequence is a 1. The next element is a 1. Third element is a 2, fourth element is a 3, fifth element is a 5, sixth element is an 8, seventh element is a 13, eighth element is a 21, and the ninth element is a 34. So if you stare at this, what you notice is the rule for creating the sequence is that every element is the sum of the previous 2 elements. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, 13 is 8 plus 5, 21 is 13 plus 18, 34 is 20 plus 30, 21 plus 13. Okay. But you actually have 2 stopping conditions here, not just 1, because notice I wasn't able to start that recursion until I was on the 3rd element. The first 2 elements are fixed at 1. So what we can write for the recurrence relation here is that the Fibonacci of n is equal to the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. That's how I'm generalizing this to work for any n. But we have 2 stopping conditions. Fib of 1 is equal to 1, but also fib of 2 is equal to 1. So if I translate this into code, what I get is I say if n is 1 or n is 2. So I have 2 stopping conditions. Return 1. Otherwise, return fib of n minus 1 plus fib of n minus 2. So let me just check myself real quick and make sure that I got the correct sequence. So I'll say print fib of n for n in range 1 to 10. Okay, good. So I got that right. Seems like everything's working. But let's look at the time complexity of the factorial versus the Fibonacci. And we're going to see something kind of interesting. So let's look at the factorial of 4, for example. So the factorial of 4 actually needs to call factorial of 3, which in turn needs to call the factorial of 2, which in turn needs to call the factorial of 1, and then we reach the stopping condition and we're done. So this is actually something called tail recursion. This is really the simplest kind of recursion that you can have, because it only does one recursive call each time. And tail recursion is very easily implemented with a loop. You could see that, right? If you were to write this as a loop, you would go 4, 3, 2, 1, and then you'd be done. But we can also write it recursively, and maybe it'll save us a little bit of code. Fine. But the Fibonacci is not like that at all, because the Fibonacci actually branches out. There are 2 recursive calls for each call to Fibonacci. So in particular, the Fibonacci of 5 requires the computation of Fibonacci of 4 and Fibonacci of 3. But actually, I do the Fibonacci 4 first, so let me focus on that one. Okay, Fibonacci of, sorry, this is Fibonacci of 3 here. Okay. Fibonacci of 4 requires us to evaluate Fibonacci of 3 and Fibonacci of 2. Okay. But actually, before I evaluate Fibonacci of 2, I have to evaluate Fibonacci of 3. So I really do these calls. I do 5, then first 4 does its thing, first evaluates 3 does its thing, first evaluates 2. 2 is a stopping condition actually, so I'm finished. And then I evaluate 1 to complete Fibonacci of 3. Okay, now I've completed Fibonacci of 3. Go back up to Fibonacci of 4. It's asking me to expand Fibonacci of 2. I've finished that. Okay, that's the stopping condition. Now I go back up, I've able to finish Fibonacci 4, I go back up to 5. Now I'm supposed to expand Fibonacci of 3, which requires 2 and 1. Same thing, it does 2 first, but finds it's the stopping condition, then it does 1. So it kind of branches out in this like tree fashion. And actually, just like when we were looking at the towers of Hanoi, there are 2 recursive calls for every call of Fibonacci. So we should expect like a 2 to the n. You could prove by induction that this should take big O of 2 to the n to compute. Because it's just branching out by a factor of 2 each time. Okay. But the thing is, if we look at this tree that's showing all the expansions here, you know, so we do 5, 4, 3, 2. Okay, then we do 2. It's a stopping condition, and then we can fill in 3. At this point, I know what 3 is, so I'm going to go on, and I'm going to then say 2, and I'm going to compute 4. And at this point, I know what 4 is, and so, okay, fine. And so if I remember what I've done, once I get here, I don't have to do that again. I already figured out 3 in the process of computing 4. So I don't even need to do that again. And actually, you know, I can cut out even more. So let's see. So I go down here, I do 2 first. I can remember what 2 was, can remember what 1 was, remember what 3 is. And then when I go to finish 4, well, I just remember what 2 is. I didn't even call it. I just remember it, that was that. And now I get to try to complete Fibonacci of 5, and I see that I'm supposed to do Fibonacci of 3, but I already did that. Just go back and remember what I did. I could cut out this entire branch here. Okay, so you can see, and you can imagine this thing's going to expand more and more, so the more I can cut out, the better. And so this will actually bring it back to a linear time complexity to match the factorial. So let's see how we might remember some of the previous results in code. So I'm just going to focus on the Fibonacci now and see if I can compare my original implementation onto a faster one. So I'll call this, I'll start with this one, I'll call it fib slow, because I know it's going to be slow. I'm going to pass along a counter as well, because I'm going to count the number of calls. So, and I'm going to make this an array because I need it to be passed by reference instead of by value, so that it actually is the same for all of them. This is like C++. I'm kind of kind of hacking Python to make it a pointer. So, but anyway, it's going to be an array. Every time I call this, it's just an array with one element. I'll add 1 to it. Okay. So let's see. Let's just make sure this works first. So if I print fib slow, so I'll say, okay, my counter starts off at 0. I'll go ahead and say, let me do fib slow of 5. I'll pass along the counter, and then I'll print how long it took. It's complaining because I need to pass. Whoops! I need to pass the counter as a parameter here. Okay. Let's see. Oh yeah, and then I also need to pass the counter along to every call of fib. Okay, there we go. What is it complaining about here? It takes 1 position argument, but 2 were given. I need to. It's fib slow. My bad. Okay, I call this fib slow. Okay, so I see it takes 9 steps. Does that match what I had drawn out here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. So that matches. What about when I cut out the tree? So let's now figure out how do we make a faster version of this. So I'll call it fib fast. I'll start off doing something similar. But now I actually want to pass along another thing. I'll call it my memory. So what I'll do is my memory, this is going to be a dictionary. So I'm just going to specify that memory is a dictionary from n to the result. Okay. So I'm still going to add 1 to my counter, but what I'll do is I'll say if n minus 1 is in my memory, then I will return that instead. So let me see. So I'll say so part 1 equals 0. So I'll say part 1 equals my memory of n minus 1. So that's my first part of the Fibonacci. Otherwise, I actually do have to do the recursion. I haven't done it yet, so I can't remember it. In that case, I will say part 1 is equal to fib fast n minus 1 counter memory. I have to pass along my counter and my memory along for the ride there. Okay, now I'll check to see, is n2 in my memory? Oops, I meant to say in. If n2 is in my memory, then I'll say part 2 equals memory n minus 2. Part 2 equals 0. Otherwise, I do have to do the recursive call because I haven't done it yet, so I can't remember it yet. So we'll say here n minus 2, part 2. And then the result is part 1 plus part 2, so I'll remember that. I'll say my memory for n is result, and then I'll return the result. Okay, I think that will do it. So let me just check to make sure that this gets the same answer, and then we'll compare the number of steps. So fib of 5 should be 5. I'll start off passing an empty memory, so just an empty dictionary. Okay, this one only took 6 steps. Does that match? Let me see. 1, 2, 3, 4, 5. Yeah, it's a little. Okay, these were stopping conditions, so I might have disagreed slightly, but that's the idea. So let's now compare a much larger number. So Fibonacci of 10. Okay, this took 109 steps. Here, this only took 55. Let's go up to Fibonacci of 100. Okay, this is going to take a while. Maybe I shouldn't have done that. Let me do Fibonacci of 20. Okay, that takes about 13,000 steps. Whereas here, that only takes 21 steps. Seems a lot better, right? So this is going to be have 2 to the n complexity. This is going to have big O of n complexity. Big O of n is way better than 2 to the n. Okay. So there's just one last thing I wanted to point out with memoization, which I'll have you finish in a little exercise. It's really something a little more about the Python language than anything else. And then I'll use memoization in the service of a very important application called string edit distance. And that's how we'll end up the module. Okay. let's go back to our Ackermann function for a moment. And so I had some stuff here printing out what the Ackermann function was doing. It's complaining here. Let's see, it's having a problem on res is equal to n plus 1. Oh, because of course I need to return the result at the end. Okay, somehow I didn't copy that line. It's returning none. So by the way, this is a good opportunity to point out that in Python, if you forget to return, it returns none. So that's how you can catch these kind of bugs. All right. Anyway, so this is Ackermann of 2, 3. So one thing you notice here is that, okay, Ackermann of 2, 3, that requires me to compute Ackermann of 2, 2, which requires a whole bunch of other stuff. But actually later I end up needing Ackermann 2, 2 again. Let me see where. Well, that's just telling me what Ackermann 2, 2 is. Yeah, but I end up wanting this again. Well, actually, an easier example. Let's see, Ackermann 1, 1. How many times does that get repeated here? A bunch. Okay, so I should be able to save work if I remember. Now the trick here is that it's really just a syntax thing with Python. If I'm going to pass along a memory, then somehow I have to have the memory store 2 numbers instead of 1. Well, you saw a trick in the first assignment where you can convert 2 coordinates into a unique number. But actually, there's another thing you can do, which is use something called a tuple. So what I can say is, if the Ackermann of, or I could say if mn, n comma n, in these parentheses, this is a tuple. You can't do this with a list, but a tuple is something called immutable, which is required of keys in your hash map. What it means is this tuple cannot be edited. So actually, let me show you that real quick. If I go to create a tuple, if I say x is equal to 1, 2, for example, and I try to say x, if I try to reassign x0, it's going to yell at me. I say tuple does not support item assignment. So this satisfies a requirement. A tuple in Python is immutable, which means that you can't change the entry. So it can be used as a key because the keys shouldn't change. All right. So what I can say, I can say if the Ackermann, or if mn is in the memory, return memory mn. That may save some time. Okay, so I'm going to have you finish this in the exercise.